Welcome to the future.
Welcome to the Muxall Open Internet of Things video blog. I am your host, Michael Crane. In today's video, we're going to take a close look at our $10 OSEPP IR detector to see how it works and how it's designed. In the following video, we'll see if we can take the OSEPP design and make it better and hopefully cheaper. But before we get started, let's review what an IR detector is and what they're used for. All right? An IR detector uses an infrared light source and an infrared light sensor to trigger an event. In the first configuration, the light source is pointed directly at the sensor. In this configuration, the sensor is always detecting the IR light unless something moves between the source and the sensor to break the light beam. In the second configuration, the light source and sensor are perpendicular to each other. In this configuration, the sensor cannot detect the IR light unless an object moves close enough to the detector to cause the IR light from the source to be reflected back into the sensor. This is called reflective sensing. So what are they used for? Well, for my application, the movement uses an IR detector to detect a hand waving over its top to turn off alarms and timers and that sort of thing. Okay, so the OSEPP IRD features include Arduino compatible, meaning it supports 5-volt TTL output, a frequency adjustment pot, a distance adjustment pot, and an indicator LED showing the detected events. Not bad for a $10 board. OSEPP also claims that the user, quote, can adjust the frequency to avoid interference with other detectors or other IR sources, end quote. We're going to get back to this claim later in the video. I use the OSEPP IR detectors, and they work well for my application. But let's take one for a test drive and see how well it really works, okay? I have the scope connected to the cathode or negative side of the IR LED, and the voltmeter connected to the anode or positive side of the LED. The scope is monitoring the carrier frequency and is DC coupled. The voltmeter is monitoring the RMS voltage, and the power supply is measuring the current draw. I'm starting with the distance D trim pot. According to the instructions, turning the D pot clockwise will increase the distance. As I turn the distance pot clockwise, we see the current draw going up, the square wave getting smaller because the DC offset is increasing, and the RMS is going up. At 18 milliamps current draw, we see the indicator LED staying on. This is due to light scattering from the source IR LED into the housing of the IR sensor. However, I keep turning the D-pot clockwise until we get to the maximum current draw of 31 milliamps. At this point, we've lost our scope trigger, and the RMS is almost 5 volts DC. This suggests the IR LED is transitioning from full current to almost full current, but it's still enough of a flicker to be detected by the sensor. Okay, so that's good. Now, I'm turning the D-pot counterclockwise to reduce the distance. It looks like 9 milliamp is the minimum current draw. However, that's not enough current reduction to prevent my hand from being detected 4 inches over the detector. Turning the frequency F-pot clockwise reduces the frequency of the carrier signal. The frequency is the modulation of the IR light, not the actual 940 nanometer wavelength of the IR light, okay? The lowest frequency I could get is about 39 kilohertz. One startling discovery is that with the frequency set to 39 kilohertz and the distance still at its minimum of 9 milliamps, the hand detection distance increased from 4 inches to 20 inches. Now, I'm turning the F-pot counterclockwise to see what the maximum frequency is. As I increase the frequency, I notice the hand detection distance dropping. So, I have to start increasing the distance using the D-pot while increasing the frequency. At about 53 kilohertz, the IR sensor stops detecting the hand wave no matter how much D I add. Now, I'm connecting the scope to the output of the IR detector. The scope is DC coupled, so we should see a drop from 5 volts DC to 0 volts DC when the sensor detects my hand wave. I set the scope to falling edge trigger and single shot capture. Okay, that looks pretty good. I grab my TV remote to see if it can be used to trigger the IR detector. Sure does. I noticed the indicator LED flashing when I triggered the detector with my TV remote. TV remotes pulse the carrier wave to encode data for transmission. So by adjusting the scope, we can see the data coming from the TV remote. However, for what we are doing, we don't really care about what data the TV remote is sensing. What we care about is that OSEPP claims the frequency of the detector can be adjusted to avoid interference with other detectors or IR sources. All right. The IR detector is set to 41 kilohertz, close to the minimum. So I'm using the F-pot to increase the frequency to the maximum of 52 kilohertz to see if we can still detect our hand wave, but not detect the TV remote. No. If it detects our hand, it still detects the TV remote, which means it would detect reflected light from other nearby OSEPP boards too. Since the OSEPP IR detector is open source, we don't need to reverse engineer the PC and create our own schematic. We can just download it from the OSEPP website at www.osepp.com, which is very nice. Looking at the OSEPP IR detector schematic, we see that they are using a 74HC quad NAND gate and a HS38B IR sensor. I have the data sheets for the TI quad NAND gate and for the Vishay SH0038B IR photo receiver. I'm not sure OSEPP is using real TI and Vishay chips, but I'll assume they are. Starting in the left side of the schematic, we have an astable multivibrator. It uses an RC circuit for the timing of the multivibrator. The variable resistor RP2, aka pot, is what we are using to adjust the frequency of the IR LED from 39 kHz to 52 kHz. The output signal of the multivibrator, which goes into the input pin 9 of the 74HC. Looking at the middle of the schematic, we have 5 volts VCC going into RP1 pot, like an adjustable current source. Then it goes into the IR LED, then into a 47 ohm resistor, and finally into the output pin 8 of the 74HC. I was scratching my head with this for a bit, but after looking up the reference in the Art of Electronics, I see that this is a legitimate way to sync small amounts of current for indicator LEDs. Okay, so looking at the right side of the schematic, we have pins 1 and 2 of the 74HC tied to ground, which means pin 3 will always be high, or 5 volts. All right? That's okay because, according to the 74HC spec, unused input pins on the 74HC should either be tied to ground or VCC, so no problem. From pin 3, we see it is supplying 5 volts to R6, which goes to our blue, well, it says blue on the schematic, but on our boards they're actually red, LED. And then to R7, which is tied to ground. It is also pinning pin 10 of the 74HC high. Pin 10 is always high, or 1. Our square wave from the multivibrator oscillates between 5 and 0 volts, or 1 and 0. So, when pin 9 goes high, pin 8 goes to 0. Basically, it's inverting our output signal from the multivibrator, and it's syncing about 25 milliamps of current to turn on our IR LED. Looking at R7, a 10K ohm resistor going to ground, made me scratch my head trying to figure out the purpose of this circuit. The only thing I could think of is that it's keeping pin 3 of the 74HC in conduction. For what reason, I don't know. Moving on to R6, a 1K ohm resistor, it is limiting the current feeding our quote-unquote blue LED. The other end of the blue LED is tied to the output of the IR detector and to the output of the HS38B IR sensor. When the HS38B IR sensor detects 950 nanometer wavelength light, modulated at 38 kilohertz, it sends a current to the base of the NPN open collector transistor, which then shorts the output to ground. A basic transistor switch. Since the blue LED is connected to the output, the current flows from the LED through the transistor to ground and lights up. This also provides the 0 or low to the microcontroller to let it know that the IR detector has detected something. Okay, that's good. The bottom part of the schematic is just showing the bypass cap added to the VCC to smooth out any power supply ripple and how the header connector is wired. Well, that's about it for this video. If you like this video, give it a big thumbs up and hit the subscribe button. That really helps. If you have any questions or comments, leave them in the comments under the video. I'll see you next time.